Hello and welcome to my presentation. I am Iris van Zelst and I will be talking to you about the effect of multiple splay fault rupture on tsunamis. So what are splay faults exactly? Well, here you have a little figure of a very simplified subduction zone. You have the megathrust, which is the main interface between the subducting plate and the overriding plate. And in the accretionary wedge, you then have faults that splay away from the megathrust, called splay faults. And as you can see, these faults are steeper than the megathrust. We can again look at this in this figure here, a bit more simplified with one splay fault. And if the rupture goes on the splay fault, you can imagine that with the same amount of slip, you will actually get more vertical displacements here than you would have if the rupture stayed confined to the megathrust. So that would look something like this. You would get a larger seafloor uplift due to slip on the splay fault. And this means, since there is water on top of the seafloor, that you get a tsunami with a higher peak. So therefore, the theory is that splay faults are quite important in tsunami generation. So what we are going to do is we are going to build on the work that we have done before in Van Zelst et al. 2019 in JGR. And we're going to add a tsunami propagation and inundation model to our modeling framework there and apply it to splay faults. So what exactly was the modeling framework that we had? Well, we had a geodynamic seismic cycle model, which we abbreviate as SC on this presentation. And we're going to use the output of this SC model for one particular event and use it as input for the dynamic rupture model, which is abbreviated by DR in this presentation. And what we're going to do in this work, what is new in comparison to what we showed in Van Zelst et al. 2019, is that we're going to use the output of the dynamic rupture model, the surface displacements, as input for the tsunami model. And this is all a 2D modeling framework, and the tsunami model is 1D. Okay, so where do we start? Well, we start at the geodynamic seismic cycle model. We have this model. You can look at the paper if you want to. And what we see is that there is a lot of yielding in the accretionary wedge. Here I plot the viscoplastic strain, and these dark colors here indicate that in the accretionary wedge, a lot of things is happening. From this yielding, we pick 6 blind splay faults. And that looks like this. So here, for simplification, I plotted the accumulated slip because that's a bit more tangible in seismological terms. And from that slip, I picked 6 different splay faults numbered here, 1 to 6. And now that we have this model, we can make our dynamic rupture model setup. We use everything from the seismic cycle model, the rock properties, the stress field, the friction parameters or the strength of the rocks, and the fault geometry. And previously we only used a megathrust, but now we also have these 6 splay faults. Okay, so what do we see? Well, let's have a look at the rupture evolution. What we see here is the distance along the fault, and then we plot on the y-axis time, and we show in this space the slip rate in color. And here we have our reference model, which is the megathrust rupture without any splay faults. So this is the model that you can find in this 2019 paper. And here we have our new model where we include these 6 splay fault geometries. And what you can see is that although it looks quite similar, the slip rates on the megathrust here, because we are showing the megathrust here, are lower in the model including splay faults. Why is that? Well, because all 6 splay faults are ruptured during this event. So we can have a look at that here. We plot our 6 splay faults numbered here, 1 to 6. This is again the distance along the fault, with 0 being near the surface and this being at depth. And we can see that there is slip on each of the 6 faults. This dotted line indicates when the main rupture front first encounters the splay fault. And as you can see, sometimes it actually activates the splay fault, such as here. Other times, we have activation from the surface because of the reflected waves that go back onto the splay fault and induce a stress change there. And sometimes it is only afterwards through a combination of reflecting waves and dynamic stress transfer. The fact that these splay faults rupture has, of course, an effect on the slip. First of all, we observe slip on each of these splay faults, and we see a decrease in slip on the megathrust. So that is what we see here. We have our model without any splay fault geometries, where the slip distribution looks something like this. And here we have our model including the splay fault geometries, where all the 6 splay faults actually rupture. And we see that if there is a splay fault indicated here by the vertical line, we have a discontinuity in slip. Some of the slip is accommodated by splay faults. The only time we do not see that is with splay fault 5, and that is because that splay fault is not activated by the main rupture, but instead by the reflections from the surface. So we do observe slip on that fault, but it doesn't take away slip from the megathrust. So we now know that all 6 splay faults can actually rupture within one event. But what is the effect on the surface displacements? Because this is what we're interested in if we want to say something about tsunamis. Well, we can have a look at the surface displacements. Here I first plot in green the final vertical surface displacements for the model without any splay faults. And as you can see, it's fairly uniform at around 5 meters. And then if we plot the model including splay faults, we see these quite high peaks, as you can see here. And these peaks correspond to the surface expression of the splay faults. So rupture on splay faults actually increases the amount of vertical surface displacements, as was indeed what we had expected. Now, how does this influence the tsunami? Well, we can have a little tsunami model that we add after the dynamic rupture model. And we're going to use a one-dimensional tsunami model setup. So this is very simple, the initial ocean height and the bathymetry. And then we're going to use the time-dependent surface displacements of the dynamic rupture model as input for the tsunami model. When we do that, we see the following. First, again, for the model without splay faults, it looks like this. And we see a rather broad wave going towards the beach. This again is distance from the trench with time, plotting the sea surface height here. And this rather large broad wave goes towards the beach and results in inundation there. If we look at the model with splay faults, we see that there are multiple wave crests. Actually, there are 7 main ones, where 6 of them correspond to the 6 splay fault geometries, and the last one corresponds to the shallow tip of the megathrust. And this then results in a much more complicated inundation pattern. Most notably, we get 2 episodes of flooding. And we can see this even better if we look at some time evolutions for different points. Here we see for a point in the ocean how the sea surface height develops. So we see in blue the model including splay faults, and in green the model without splay faults. And we see one, well, more or less one wave for both. But then at the coastline to be exact, whereas the model without splay faults shows one real inundation flooding episode, we see 2 flooding episodes for the model including splay faults. And if we look a little bit further on, actually at the beach, we see this again. So what have we now achieved in this project? Well, We can model tsunamigenic earthquakes and the resulting tsunami over a large range of timescales by using what we had before. We can now model geodynamics, to seismic cycles, to dynamic rupture, to actual tsunamis in 2D with our modeling framework. And we apply this modeling framework to tsunamigenic earthquakes and splay faults. And we find that rupture can occur on multiple splay faults during one single event. And if this happens, rupture leads to larger surface displacements and tsunami heights and different inundation patterns. Thank you very much for listening.